Cool. Let's dive in. And so for the second speaker, we have the pleasure to have Aymeric Capitaine, who's going to talk about unraveling in collaborative learning. The floor is yours.
Thank you. So, hello everyone. I'm Aymeric. So we've been working on this project with all of my ocean supervisors. So Madi, Alain, Etienne, Eric, Michael, and Antoine for sure. So yes, I'm going to speak about unraveling collaborative learning. So maybe the first, oh, don't know how to change the slide. Okay, so the first question to ask is, what is unraveling? So actually unraveling is a quite well-known concept in microeconomics. I'm not sure every one of you have heard about that. So that's a notion which is due to George Akerlof, who won the Nobel Prize in economics for that. And to exemplify this concept, I'm going to use his famous example of the market for lemons. So here, lemons does not refer to the fruits, but it's an American slang word for very bad quality second-hand car. So the kind of car you start to buy. So imagine that you want to buy a new second-hand car. You have a reservation price, say you're ready to pay 10,000 euros for your car. But you are faced with some cars. Some of them are very bad, some of them are very good, but you don't know which is which. Okay, so because there is a non-null probability that you end up with a lemon, a very bad car, you will bid a lower price than your actual reservation price. Okay, so that sounds normal because you maximize your utility and expectation. But this has very, very sad consequences. The consequence is that the best car on the market will leave the market, okay? Because the seller won't be willing to give away his car for such a low price, okay? So the good car will leave the market. But then this will reinforce your fear about the quality of cars because you'll know that you're only left with bad or medium quality cars. So you will bid an even lower price. And this will go on, it will crowd out another car, and so on and so forth. So the market will enter a death spiral up to the point that you are only left with the worst cars on the market. Okay, so that's the historical example. So another market which is famously known for being subject to unraveling is the insurance market. So here is another economist who won the Nobel Prize for that, along with Akerlof. And so why is that so? So imagine that you are an insurer, okay? You want to sell some insurance to people. The problem is that you do not observe their habit of life, whether they smoke, they drink, whether they eat well. So you know that some people will cost you a lot because they will, unfortunately, end up with disease. So because of these people, you will have to increase your fees to still make a positive profit, okay? But if you increase your fees, what will happen with people with good health outcome? Well, they will leave the market because they won't be willing to pay such a high price insurance for a risk that does not concern them. So this will reinforce your fear about the average quality of the insuries. You will increase your fees and so on and so forth. And once again, your market will basically explode because of this very information asymmetry about the health outcome. So just a fun fact. So I won't go into the detail of this graph, but that's the classical way to depict unraveling. So some empirical studies have been made in the United States. And this study, for instance, found that in the United States, there is basically no insurance market for people above 70 years old because of unraveling. Okay, so that's something which exists and which is quite serious. So if you want to be a bit more formal, the unraveling à la Akerlof, because there are other concepts of unraveling, refers to a market in which the only Nash competitive equilibrium, so I don't know if this notion rings a bell to everyone, but basically that the equilibrium of the market from which you don't deviate, only have the worst quality goods which are traded because of the information asymmetry. So we are in statistics, so the question we want to address is whether unraveling could occur in collaborative learning. And that's a question that sounds consistent, because if you think about it, when you set up a collaborative learning task, you just mix people with different data. People don't know the quality of data of others, so you may end up with the same information asymmetry problem, and your collaboration may explode. We hope not, and that's exactly the subject of this study. So this is our framework. We consider some data which are distributed according to distribution P0, okay? And we consider a bunch of agents who want to perform a prediction task over this data. So they want to pick an hypothesis lying within a class around J so as to minimize the population risk with respect to some bounded continuous loss L, not continuous, just bounded actually, with respect to P0. Okay? And we assume that our hypothesis class obeys the classic path bound, so of this form. You know that the actual risk, the empirical risk, does not deviate from the population risk too much with respect to this rate. So you can think of this bound as being motivated by pack bias theory, for instance, or Rademacher theory in case of classification. But that's something quite flexible. Okay, and the fun comes from the following slide. We assume that the agent do not have directly access to P0, but to some PJ, which is not exactly P0. So you can think of this PJ as the consequence of having bad quality sensors or having bad experimental conditions. You do not directly sample from the actual distribution you are interested in, but there is always a small noise. Okay, and so how do we capture the quality of the distribution? Okay. How do we capture the quality of the distribution PJ as we would like to capture the quality of the car? We use this divergence. So theta j captures the quality of the distribution, and so basically it is the worst difference in risk between the risk under PJ and under P0. So intuitively, this divergence captures the bias you have when you sample from PJ, but you want a model which performs well with respect to P0. Okay, so I did not invent it. That's come from the domain adaptation literature. So it has two interests. First, theoretically, it works very well with pack bound because you see that there is a uniform flavor with this sub. And also it is very practical because you can easily estimate it in the classification case. So that explains why this divergence is famous and why we use it. Okay, so now that we have our framework, let us introduce the proper coalition setup. So each agent has two possibilities. So first, they can join the coalition. So they can.
Ouais,
Yes.
Joachim, je vais venir rendre.
I think someone has his microphone opened. So yes, our agents can first join the coalition, so decide to collaborate. So how does that go? So any agent J samples some data points from their PJ, okay? Then all the samples are pooled together by some aggregator, okay? Then a model is trained through empirical risk minimization over this pooled sample. Okay, so you have this wonderful graph. Everyone gives some data and then receive back a model. Okay, so a natural question to ask is, what is the quality of the resulting model? Because you mix different data with different quality. So you can show that the model, the resulting model, obeys this pack bound. So R star here is the optimal risk you can achieve within your hypothesis class. And you have a risk excess, this epsilon, which decreases with the total number of data you gather from your coalition. That sounds quite reasonable, but increases with this theta lambda, which is the average type within your coalition. Okay, so if you make people with bad data quality collaborate together, this term will become big, and so your model will be worse. Okay, so that's just the way we capture the quality of the model resulting from the collaboration, and this quantity is key. Okay, and so if you join the coalition, just as Niva Zini assumed, we have some utility of this form. You do not enjoy having a large statistical risk, okay? So here it's the best risk plus the risk excess. And you do not want to sample too many data points because you pay a price for this. Okay, so that's the first choice. You can join the coalition. Or if you don't find it interesting, for instance, because the collaborating model is very bad, you can remain on your own. So pick the outside option. And so basically, you draw some samples from your distribution PJ, you train a model over that, and then you remain on your own. Likewise, the model will obey some pack bound with here your own type instead of the average type, okay? And you will enjoy a utility of the same form. The risk of your model, so with a minus because you don't want a too high risk, and the cost, the total cost of it. Yes.
Do we have the same curves for sampling your own data and sampling your own data and sharing it?
That's a very good point. So we did not add some costs related to privacy, for instance, or we could, but I think it wouldn't change a lot the problem. It would certainly just translate a bit the quantity. But here we assume that for the sharing cost is no. That's a good point. Okay, so no. Yes, sure.
Again.
Yeah.
Like you do not know like the type of your coalition, right?
So that's another very good point. Here we were interested in theoretically observing the unraveling phenomenon. So we assume, and that's quite unrealistic, that agents know their type.
Yeah, okay.
But as I said, and as I will show you after, it's really easy to estimate the type. So we could do estimation instead. So it would add an epsilon with some delta probability because you will have an estimation. But here, just for analytical convenience, we assume that types are fixed and at least known by the agent. Okay. So they sound reasonable. You may know
yeah, but you
data.
would do like something as neat as you get down. Like you would do exploration.
Exactly. The project would become much more clever, but much more complicated. So, well, the first question we could ask, knowing that we have this framework, is what is the best collaboration we could set up? Okay, so imagine that you know the type of everyone. Everyone knows the type of everyone. What is the best thing we could opt for? So to answer this, we would need to solve this optimization problem. So I didn't introduce all the notation. So here is small cheat sheet. So the upper part of the problem is just the maximization of the total welfare. Okay, so you want to maximize the sum of utility of everyone, those within the coalition and those outside the coalition. Okay, so you're a benevolent aggregator. You care about the total welfare, but to find this optimal collaboration, you have to respect some constraint. So the upper one is the so-called participation constraint. So what it says is that every agent within the coalition should find it beneficial to remain within the coalition and not leaving it. Okay, so because otherwise your coalition wouldn't be stable, everyone would go away and pick the outside option. And the second constraint captures the idea that you cannot ask for a negative amount of data, which sounds quite reasonable. Okay, so this problem is not too hard to solve, and so here is the solution. So imagine that all the agents are sorted by decreasing quality. Yep. So the decreasing quality type. Sorry. So the best agent are on the left-hand side, and the worst agent in terms of theta are on the right-hand side. And so what is the solution? Well, first of all, you only collect data from the best agents. Okay. So to the some function of the convergence rate. Okay. So you only ask them to contribute. And how many data points you require from them? Well, you require the number of data points which will make them still willing to remain within the coalition. Okay, so if you ask for too many data points, they will basically leave the coalition because they will be better off alone. Okay, so you just ask them the threshold. So you another time you make the participation constraint binding. Okay, and then you train a model over their data and you give back the model to everyone. Okay, so why is that optimal to do so? Well, first off, you only ask data to some agents, so you spare any sampling cost for all the others, so they are happy. And why do you ask only the best agent some data? I remind you that the pack bound we found about the collaborative model depended on the average type within your coalition, so you only ask the best one to contribute, so you have a very good model. Okay, so that's the optimal solution, the upper bound of welfare you can achieve. Okay, so now the interesting question, and the one which will lead to unraveling, maybe not, see, is when information is hidden. That is, the quality index is only known to the agent. Okay, so that's the realistic setup. For either legal or competitive reasons, people do not share the information about their data, sorry. So if you want, you're an aggregator, you want to set up a collaboration, you will most likely end up in this framework. Okay, so now that we do not know the quality index of people, we cannot do the solution before, because I remind you that the data we asked depended on the quality of data. So what is the first idea that may come to mind? The most natural one is just to do as before, but you ask people to declare their type. Okay, so let's be in the skin of a naive aggregator. You just ask people whether they want to remain on their own or participate. Okay, so let's say that the red one remain on their own. Okay, goodbye. Then you ask the other their quality type. Okay, so they declare it. You are very you trust a lot of people. So then you apply the contribution scheme we described right before. So you ask for some contribution. Okay, and then you give back the model based on this contribution. Okay, so that sounds quite natural. But what could go wrong? Do you have an idea?
I have a question
Yeah.
before.
Yes.
The guy that the people that do not want to participate, they say that nothing.
So they resort to their outside option, so they will train a model on their own.
About they do not decide. They know anything about the coalition, so they do not know if it's.
Oh yeah, so yeah, it's a bit misleading. Everything is a one-shot game, so
Okay.
everyone takes the decision simultaneously.
Okay.
Yeah, it's not sequential, as this slide could let think. So do you have an idea of what this aggregation is very bad? Yes?
People cannot.
Exactly. The problem will be here, okay? People can and actually will lie. Because I remind you that the very, very, very good agents are not asked too many data points, okay? That's very, very thin arrow because their participation constraint is very low. So if you ask too many data points, they will go away. So everyone, every contributor will have interest in saying that they are very, very good. So they won't be asked too many data points, okay? And this will be critical because if everyone lies saying, oh, I'm the best, then you are not able to distinguish people. Okay, so you will ask uniform contribution and you will end up with a very bad model. So every good data owner will decide to remain on their own. Okay, so that's the intuition. And indeed, we found that in any pure strategy dominant equilibrium, so once again, if you're not too familiar with game theory, that's just a strong and a very stable equilibrium concept, the coalition is either empty or made of the worst data quality owner. So that's exactly the unraveling we found with cars. Okay, so or not, actually, it happens. So the takeaway of this is that if at some point you want to set up a collaboration, just be careful about quality of data, because if you face strategic agent, they will all leave the coalition. So know that we found that unraveling will crush us. The natural question is, what can we do to fight this? Okay, how could we help to restore optimality? So if you're a bit familiar with mechanism design literature, you will know that two properties are required to restore optimality, and those two properties are incentive compatibility and individual rationality. So what is incentive compatibility? It basically says that it must be for any individual not good to lie. That is, if you tell the truth, so if you declare your actual type theta, you're at least as well off as you'd be lying. Okay, so that's really something that prevents you from lying. And individual rationality basically says that you don't want to leave the coalition. Okay, so you want to remain in the coalition. That's encoded with this little one here. And so if you do so, you're better off as compared to the situation where you remain on your own, which is encoded by the 0. Okay, so with these two properties, people don't want to leave the coalition, that's the one on the right-hand side, and people don't want to lie, meaning they will be in the coalition with their type. So we recover the optimal coalition as a Nash equilibrium. Yes? That's a good question, and we'll see right after. So That's just a goal, okay, we want to achieve. And so perfect, thank you for the transition. How to achieve this goal, how to achieve these two properties. So once again, if you know a bit microeconomics, you may have heard of the VCG mechanism. So that's a very old idea which traces back to Vickrey in the mid 20th century. And so the VCG mechanism is a very simple idea. You make everyone participate, but you make them pay the cost of their very presence. So that might sound a bit cryptic, but if you look at the formula, you will pay the utility of all other guys. Sorry, that should be a K, not a I. Of all other guys when you're here, okay? Then you take away the person K, you check what is the best allocation you can find, and you take away the utility of everyone. So that's really this, and captures the externality you exert on other people by simply being here within the collection. Okay, and by doing so, it can easily be shown that you realign the individual optimization problem with the global one, so everyone finds it in her interest to say the truth. Sorry if it's a bit fast, but that's a very interesting concept. So that's the usual way economists manage to restore individual rationality and incentive compatibility. Unfortunately, we cannot do it in our case. Why is that? So because for the very, very good individual, you will need to pay a strictly positive PJ to them. Okay, so you will have to make a strictly positive transfer, that is increase ex nihilo their utility. Can we do it in our setup? No, because we do not have monetary transfers. Okay, usually economists think that you can give a dollar and then everyone's happy, but here we do not have it, so it's not possible. So we have to be a bit more clever and find another way around to restore incentive compatibility and individual rationality. And we almost succeed to do it. You'll see we approximately have these two conditions with the following idea. We combine on the one hand probabilistic verification method and on the other end accuracy shaping method. So what is probabilistic verification method? That's a quite new branch in mechanism design. It's the idea that your principal, okay, so the aggregator in our case, may be able to estimate the type of people, of agents. Okay, so if you are able to estimate the type of people, you may be able to detect lies. And if you are able to detect lies, then you can punish liars. So you will prevent them from lying. And so you may hope to restore truthfulness. Okay, so in our case, what would be the estimated type? It would be this quantity. So we come back to your question, Antonio. This is a very good estimator actually of the type. It behaves really well. So that's why we took this notion at first. So if we had some samples from the actual distribution, P0, okay, very few ones, we do not need that many, we can estimate the type of everyone. Okay, so that's the first ingredient of our method to recover ICIR. And the second ingredient is accuracy shaping. So that's actually an idea that's come from Pranit and Michael and other from Berkeley, who are maybe listening. So the idea is that you will degrade the collaborative model you give back to people according to the line. Okay, so I will not give you back the collaborative model, but I will give you back a personalized version, which will have a risk excess that depends on your estimated lie. Okay, so the idea is that if you lie to me in the hope of not being asked too many data points, then I will give you back a very bad model, so you don't have interest in it. Okay, so that's a lot of words. Let's see with small drawing what our new mechanism looks like. People decide whether they enter or not the coalition. Okay, they declare that type, so they may be lying. You ask them data according to the optimal contribution scheme. Okay, but then critical step, you estimate their type based on the data they give you. Okay, so you have here in purple an estimate of the lie they made to you. Okay, then one second. You give them back a model which is as bad as the estimated line. Okay, if you lie to me a lot, then you will have a very bad model. So you do not have interest in line. Yes, Stan, you have a question?
Especially estimating the quality of the data is, or the agent is based on having some true sample.
Yeah.
This, I imagine, is used by estimating which are the best agent, which will have sample close to true. Yeah, the
Yep.
true probability distribution. And how do you take that into account?
So I take that into account at this step when I ask for data, because so you declare a tape, I ask for data according to your the tape you declared, and then I'll give you back a bad model. So oh yeah, maybe so I didn't quite get what you said. You said that we should take advantage of this to only keep the best agents, right? That's your idea.
That's this is made by assuming that you have real good samples.
Yeah.
How do you know you have some?
You mean this one, the Z0?
Yeah.
That's an assumption. Imagine that the statistical prediction task at hand comes from some data generating process that have some past realization. So this may happen. Like for instance, imagine you are trying to share data about meteor, do you say weather forecast, for instance. Then you have some historical data for the forecast. So if you have that, you can implement the mechanism. Yeah, that's an assumption. That's a quite strong one in many cases, but in others it makes sense. Yeah.
So, but if someone says they're very clear,
Yeah.
then you will have few data points.
Yep.
So you have to do this comparison based on very few data points.
Exactly. So that's a very good remark. So I'm hiding a lot of technical details, but for sure, the size of the actual data points that you have matters a lot. And when you have very few, then your Nash equilibrium are very approximate. So what's
So you need to kind
yeah, so exactly. So well, I can show you in the paper if you're interested, but we need to assume that actually there are not too many samples from P0, otherwise agent will try to game this. So, but I can. Oh yeah, I don't know if everyone. So Andrea was pointing out to the fact that the number of samples from P0 is really important. Oh, you mean from the?
if someone says they are a very live blast for a few data points, just very few.
Yep.
And then you have to make this comparison based on an estimate of the risk that is just
Yep.
based on 10 points.
So yeah, so yeah, that's a very good remark. So I crop the sample up to the number of sample within Z0. So I assume that we have very few Z0 data points. Let's say you have 10 data points from the actual distribution. You declare your type. So I ask you 100 data points. I keep at random the 10, just for the two risks to be estimated on the same number of data points. It's yeah, so it can introduce a lot of variance actually. And so in the proof, you'll see in the result I will show that it depends actually on the variance of this estimator. So if you have a lot of data, you are happy. If you don't have, the result will be approximate.
Usually, you even suggest you should lie a lot. Lie a lot, then you have a super high variance. That's very few data points.
So
More difficult to try.
yeah, so as I said, we assume that the aggregator will only keep the same number of data points for everyone. Okay, so you have 10 data points from P0. I will only keep 10 data points from every contribution of every agent, because yeah, that's a very clever remark. the agent could game with the size of the sample, and so the problem would become really intractable. So that's why that's a bit that's really suboptimal, but that's the only way you can do it. Yep.
By the agents pre-train the model.
To pre-train the model.
Let's say each agent gives 10 symbols to get into position for the test.
Yep.
We use the sample to add first data points to train the model.
That's what we do actually. So we ask for data points, and then we train a global model. Yes, I didn't explain it right. That's my bad. So we train a global model, okay, which is the same for everyone, but then we send back a degraded version to everyone. Okay, so there is an actual collaborative model that is learned on all contribution, and I just send back a personalized version. Okay, so is that clear for everyone? Cool. So, yep, just a very, I think that's a horrible English mistake. I'm sorry for that. So in practice, how can we do this step? Because it might sound a bit magical. So imagine that you're in the classification case. Okay, so your Y component is either -1 or 1, and your loss is the 0, 1 loss. So this ugly quantity here, the sub over all your class becomes something which is way more tractable. You just take the sample of all your contributors. You just flip the data points. You merge it with your data points from P0. You train an empirical risk minimization estimator, and this gives you the type. Okay, so that's a very convenient thing to do in a classification case. And as for the personalized deteriorated model, in the classification case, you can simply flip a coin at every time. So give back, sorry, a random estimator where you flip a coin and you give the contrary of the prediction at some proportion, which is here. And so this will achieve the desired degradation. Okay, so that's a lot of work. Does that work well? Yes, it does actually. So it can be shown that this new mechanism is epsilon delta incentive compatible and epsilon delta individually rational. Okay, so that's not exactly the property we wanted. We are epsilon far from the property we want with high probability, but still that's an achievement. I hope so. So to come back to your question, Andrea, here the epsilon, which captures the distance from the actual incentive compatibility, depends on Q here, which is the number of samples you have from P0 and consequently from each agent. So and you see that it decreases quite rapidly with Q. So the more samples you have, the better it is. And so a very nice consequence of this proposition is the following. Under this new mechanism, entering the coalition, which is encoded by this one, and revealing your actual type, which is encoded by this theta, is an epsilon pure Nash equilibrium. Okay, so it's not exactly a Nash equilibrium, but you cannot get too much of a utility gain from deviating with high probability. Okay, so we effectively, under this mechanism, break unraveling, because I remind you that unraveling is the fact that at any Nash equilibrium or dominant equilibrium, it's even worse. You have an anti-coalition, and now we have a non-anti one with truthful people. So that's cool. And that's the end.
So there were many questions during the presentation, but do we have more? I wanted to ask if you like still a naive question, like you have like I sense that in your model you already have like competitiveness. Okay.
Yep.
So can it be addressed differently in order
Yep. So that's
in order not to have like unraveling and still have like epsilon delta?
yeah, that's not a naive question at all, actually. Here I just hidden under the carpet the fact that you only have one aggregator. Okay.
Yeah.
So you can either remain on your own or join one grand unique coalition. But if we do the parallel with insurance market, for instance, we could imagine some aggregators competing each other. So instead of just having this binary choice of joining the coalition or not, you may have a graph with people joining one coalition, joining both, etc., etc. So that's a very interesting thing, I think, to look at. So actually, in Stiglitz model, just to have his face here. So the historical study of unraveling, they consider a perfectly competitive market. So with an infinity of aggregators. So and they still have unraveling. I have no clue of whether this would still work in our case if we had many aggregators. So that's a really good question for future work.
Okay. Are there any questions? Really have plenty. So if not, let's thank Aymeric again and all the speakers today.
Thank you.
And see you in a tiny mouse.